All right, ladies and gentlemen, what I'm going to do real quick before you start into this making sense of ionization activity and trying to explain the pattern of ionization energies and what causes the these spikes and valleys and these little dips in the patterns, is I want to talk to you about some different degrees of stability that exist when we do orbital filling notation. So before you get into trying to understand the pattern there, we really need to understand one thing about electron configuration. When electrons fill the sublevels, the S, the P's, the D's, and the F's, there are varying degrees of stability that come from different ways that they are filled up. The least stable filling of an orbital or of a sublevel would be anything random, like a P1, 2, 4, a P5, for instance. They're not half filled, they're not full, they're what I would call random. They're randomly filled, and that could go for like a D1, 2, 3, 4, 6, 7, 8, 9, F 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. Any of the configurations or the fillings of orbitals where the sublevel is not half filled or full. That's the least stable. In other words, those would be the electrons that would be the easiest to get rid of. The next more stable configuration is when the S, P, D, or F sublevels are half filled, meaning every orbital has at least one electron. Even more stable than that is if you have a full S, P, D, or F. So you have an S2, a P6, a D10, and F14. And then the most stable is when the entire outer shell is filled, meaning your S and your P for that sublevel, for that energy level, are filled. So just to give you an example, let's walk through a few of these configurations, and we'll talk about where the stability is going to spike. Okay? So if we start with our 1s, and we put a single electron in it. Right off the bat, it's going to require a lot of energy to get rid of that electron because it is really close to the nucleus. So we have our nucleus, right? And that first electron is going right there. There's no shielding, really, really small radius. So that electron is going to require a decent amount of energy to get rid of. It's also a half-filled sublevel. Now, the second electron that goes in, the 1s2, that would give us a full first energy level. The 1s is all that's in that first energy level, so that's a noble gas configuration, so that has a really high stability. It's going to take a lot of energy to pull electrons away from an atom that has no shielding, very small radius, and it has a noble gas configuration. Okay? Now, after that, we come into our 2s. Okay? The first electron that goes into the 2s is going to have some shielding. So the shielding of the previous two electrons is going to make this probably a little bit easier to remove than that first electron when it was the 1s one. So that first electron, we'll just put it over here. Okay? A little bit easier to remove than the very first one because there's some shielding, but it's still, that's a half-filled sublevel, so that's going to be fairly energy consuming to get rid of. Now, when we fill up the next electron, and we put the second electron in, it's going to require some energy. Probably not as much as the helium, the second electron that we put in, but that's a filled sublevel now. So that's pretty stable. Then we get into our P sublevel. Remember, it has 3 orbitals. So you're going to have to draw 3 lines. The first electron, that's what I would consider a random filling. P1, it's not half filled, it's not filled. That third electron is probably going to be easy to get rid of. Probably going to be a little bit less than that second one. Okay. The second electron that goes into the 2p, it's random as well. Okay. So we have another random. So it's probably going to be a little bit easier. It's still the same amount of shielding. Maybe held on to a little bit tighter because we're moving across and we're starting to get a little bit greater nuclear charge. When we get to the third electron in the 2p, now we have a half-filled sublevel. A half-filled sublevel is more stable than the random one. So that next electron that goes in, man, that's going to have a little bit of a spike in energy of what is going to be required to remove it. The fourth electron in the 2p is going to be random again. So we went from random to half-filled. Now we're back to random again. So that electron is probably not going to be as hard to remove as the one that gave us a half-filled. After that, we get another electron in, and it is random, but it has a little bit more nuclear charge. So that seventh electron got a little bit more energy needed, and then the last electron in the 2p, that gives us a noble gas configuration. That's the most stable. That eighth electron in that second energy level is going to be super energy intensive to remove. You're going to need a ton of energy to get that electron out because that gives it the full S and P. It gives it a noble gas configuration. Then what happens is we go back down to an S sublevel again. So then now we're going to have one electron beyond the noble gas, which is not stable. So that one's going to be a lot easier to remove than that one. That's still a half-filled sublevel, so it requires decent energy. This one, now we have a full sublevel. So now we have 2 electrons on the third energy level. If we think about how would that electron on the third energy level compared to the one on the second, well, it's probably going to require a little bit less energy because there's more shielding. It's further away from the nucleus. It's probably going to take a little bit less energy. Then the second one, that's probably going to take a little bit more energy because now the nucleus is starting to build nuclear charge and we have a full sublevel. When we get to the 3p, that's one away from a full sublevel. So that you're going to see a drop in energy. You'll see a drop in energy, and then we'll still add that electron in. Then we still have random, but we have a little bit bigger nucleus. So the nuclear charge is a little bit bigger. So that electron is probably going to take a little more energy than that one to remove. And then we get a half-filled sublevel. So the next electron that we have in there is going to be really hard compared to those other two to remove. Then we go back to a random. So we'll probably see a drop in the amount of energy needed to take that next electron away. And then we're random again, but a little bit bigger nuclear charge. So that one's going to require a little bit more energy than that one to take out. And then finally we end up with a full S and P, which gives us the configuration of argon, which is a noble gas. So that electron right there, the one that gives us 8 electrons on the outside, is going to be really hard to get rid of. So what we want to realize is anytime you have an S that's half-filled, you have a P that's half-filled, if you have a D that's half-filled, that requires a pretty decent amount of energy to get an electron away. Okay? Anything short of those, it's a little bit easier, okay, because there's not a stability. Half-filled is more stable than random. If we have an S that's filled, that's going to require even more energy. If we have a full P, we're probably going to have a full outer shell, so that would be really hard to get rid of, that last 6th electron. And if you had a full D or an F, those guys are going to require much more energy to pull electrons from full sublevels. Okay? So with that in mind, realizing random configurations require the least amount of energy to get rid of. Half-filled sublevels require a little bit more energy to pull electrons away from. Full sublevels, a full S, P, D, or F, requires even more energy than the half-filled. And then if you have a full S and P, in other words, if your configuration ends up being the configuration of one of our noble gases, that's when you're going to have the most energy in a row is going to be needed to pull that last electron off of that
most stable configuration. So as you think through that and you look at that graph, think about the electron configurations. Think about the electron configurations as you move through these elements. Maybe do a few of them and see if you can identify the pattern. Where do these little peaks happen? And where does what causes this drop after that peak? So why does lithium drop way down low? Why is lithium lower than hydrogen? Beryllium jumps up, but then the next element, boron, drops down. Why does carbon get higher, needs more energy? Nitrogen needs more energy, but oxygen needs less. Why does fluorine need more energy? Neon needs even more energy. So neon's the highest in the second group. But then sodium, the beginning of the third group, drops all the way down here. And then magnesium goes higher, but then aluminum drops down low. What is the cause of those little peaks and valleys? And why is there a valley after every peak? So why do we go from low to high? We have a peak, and then we drop down to a valley again. We have a peak and then a valley. See if you can make sense of that using nuclear charge shielding and the stability of different sublevels.